Dear viewers, you are my greatest inspiration. You have supported me all these years. Your kind words of appreciation motivate me to keep making more videos. Welcome to my quantum physics video lesson series. There are so many key topics and subtopics associated with the studies of matter and energy at the most fundamental level, principally wave-particle duality, that I had to make 7 separate video episodes. These videos in this video series present profound insight into the quantum theories of wave versus particle in 7 distinct video lessons. This video series is a full package or information bank. The viewers are advised and encouraged to watch each and every video lesson in this series in order to perceive the background concept. These 7 video episodes are a thought-provoking journey through the subatomic world. Please note that although this video is rather compact, as a starting point, it's nonetheless offering an elaborate overview of the prime topic, wave-particle duality, explicitly presenting the theoretical aspects, basic principles, subtopics, key definitions, key concepts, along with a question-answer session, as precise and concise as possible. The way you should write in your exam answer papers. Predictions, discoveries, backgrounds, along with principal stages of breakthroughs in the history of physics research, and many more, have been explored and reviewed here. With cool illustrations, graphics, and fascinating facts. Intricate mathematical derivations are, however, beyond the scope and purpose of this video. Is light really wave? Or particle? Have you often pondered over how quantum physics is rather philosophy than mathematical derivation? Philosophy? Or physics? Well, that's what we say about cosmology. Right? The emerging conception of wave-particle duality roots back to a juncture in history where classical physics stopped. The esoteric dispute over wave-particle duality. When and how did the shift in balance of conception ensue? Ancient views about the nature of light. Wave nature versus particle nature of light, and electromagnetic wave, is an often-cited century-old esoteric debate. Isaac Newton's corpuscular view continued to receive unanimous support, as the community of erudite scholars, and academicians back then, either surmised, or conceded, as revealed in the publication excerpts. Eventually the substantial transformation, a sea change, transpired. By the 17th century, Christiaan Huygens, and then, since the 19th century, Thomas Young and Arthur Compton, turned out to be the 3 veritable instigators of the tilt in the balance of conception, which emphatically shifted the description of light towards one side or the other. Later on, Louis de Broglie, who spoke so vehemently of matter wave, played a key role in unraveling the mystery. The key periods in the history of physics research, principal historical turning points, along with the key topics and subtopics, have been eloquently reviewed and discussed here. Newton's model versus Huygens model, Thomas Young's double-slit experiment, blackbody radiation, ultraviolet catastrophe, photoelectric effect, Copenhagen interpretation, wave function collapse, Compton scattering, concept of photon, de Broglie hypothesis of matter wave, and Niels Bohr's complementarity principle have been reassessed. Link between Einstein's mass-energy relation and Planck's equation has been analyzed with a present-day philosophical standpoint, rather than intricate mathematical approach. Let's take a tour over an outline of the principal historical achievements, breakthroughs, and turning points in the history of physics research.
Coexistence of wave nature and particle form makes us rethink our perception of reality in the ordinary world. In order to comprehend the concept of wave-particle duality, one has to start with perceiving the idea of the differences between particles and waves.
Sir Isaac Newton, the most enigmatic supreme genius in the history of science, is highly regarded for his laws of motion, gravitation, and nature of white light. Christiaan Huygens was the first to describe light as traveling in waves, proposed in 1678, whilst Isaac Newton thought light was composed of tiny particles. Christiaan Huygens brought about an entire new perspective of optics. According to Huygens' wave model of light, every point, on a wavefront, is itself source of spherical wavelets. The sum of those spherical wavelets forms the wavefront. Huygens' model of light, which provided a new understanding of optics, assumes light behaves as a longitudinal wave, characterized by oscillation, crests, troughs, and amplitude. He further proposed that a primary wavefront can be perceived as infinite number of points, each point generating a secondary wavelet in a spherical manner. The interference of these secondary wavelets creates wavefronts of varying shapes and direction. Back then, this model was able to explain most of the properties of light, including refraction, reflection, as well as diffraction. By 1770, two apparently incompatible theories of light were in competition. Christiaan Huygens formulated wave theory of light. The undulatory theory that light is transmitted as waves was proposed by Huygens in 1678, and published in 1690. Newton versus Huygens. Newton was interested in light from very early on in his career. For various reasons he favored the particle theory of light, which rationalizes rectilinear propagation of light. However, Huygens supported wave theory of light, which is by far his most important contribution to science. He demonstrated wave interference, arguing that wave theory supports reflection and refraction. Now, hold on a minute, buckle up. Ready to hear something rather dramatic? Even though Newton's corpuscular model of light failed to account for color, polarization, interference, and diffraction of light, his theory generally prevailed. On the other hand, despite Huygens' commendable accomplishments, Huygens' principle wasn't even indisputably approved, or formally accepted, until Thomas Young's double-slit experiment turned up as the first firm support in favor of Huygens' wave model of light. Thomas Young first let the sunlight rays pass through a single slit on a screen to produce coherent light. This light was then projected onto a pair of parallel vertical slits, or twin slits. It caused diffraction of the incident illumination. Coherent wavefronts emerged simultaneously from each slit in concentric circles. The result of interference between the two discrete coherent diffracted light waves was visualized as corresponding variations in the interference intensity distribution patterns. Young's experiment was based on the hypothesis that if light were wave-like in nature, then it should behave in a manner similar to ripples on water. He was the one who first came up with the term interference fringes. Okay. What if we are throwing grains of sand, or salt, through the double slit? The grains will pile up in two separate clusters, right in front of each slit. Like this, right? If we hold on to the classical physics theory, it was predicted that the particle nature of light would produce results different from Young's. A beam of photons directed at the slits was expected to be separated by the slits into two parallel photon beams, simply creating two light fringes in front of either slit, just like SANS did, right? However, this did not happen. Mystery of light-emitting bodies represented an enormous challenge for contemporary physics. Blackbody radiation contradicted the theories of classical physics. In the late 1890s, calculations of the spectrum of blackbody radiation, based on classical electromagnetic theory and thermodynamics, ended up in major inconsistencies. in the matter of two specific aspects: energy and intensity. As you already know, Albert Einstein is remembered for his great relativity theory, gravitation, as well as his legendary mass-energy equation. However, neither of these accomplishments brought him the Nobel Prize. He received that honor for his theoretical work in quantum physics. When we look back to the 1920s, the Copenhagen interpretation was first posed by Danish physicist Niels Bohr. The founding father was Niels Bohr, along with Werner Heisenberg, who also made important contributions. Please bear in mind that the Copenhagen interpretation was the first comprehensive attempt to perceive the world of atoms, represented by quantum mechanics. Through the 1920s, the central ideas of the Copenhagen interpretation were developed by a core group of quantum physics pioneers, centered around Niels Bohr's Copenhagen Institute. We welcome you to come over and explore academic career opportunities at the Niels Bohr Institute, inaugurated March 3, 1921, by Professor Niels Bohr in Copenhagen, Denmark. The Niels Bohr Archive is an international research hub for the history of physics, Niels Bohr's life and work, and its philosophical implications. It holds an extensive archival collection of original documents, manuscripts, letters, photographs, research records, publications, centering on archival records of historical events, such as Copenhagen interpretation, and of course, Bohr-Heisenberg meeting 1941. Enthusiastic viewers worldwide are welcome to apply for access, funded projects, for participation in ongoing research, and historical tour of this glorious institute. Please come, visit, and make your career at the Niels Bohr Archive Copenhagen, place for study, research, and outreach. Let's begin telling this amazing story in 1922, when compelling evidence of the particle nature of electromagnetic radiation was found by the American physicist Arthur Holly Compton. However, Compton wasn't the only one. I would like to highlight the fact that although Max Planck and Albert Einstein postulated conceptual background, that light can behave as both wave and particle, it was actually Compton who finally provided evidence that this is possible. In this context, I would like to mention that Louis de Broglie is the first person to receive a Nobel Prize on a PhD thesis. Scientists were still skeptical about how both matter and light are somehow both waves and particles, simultaneously having variables like wavelength, which is a wave property, as well as momentum, which is a particle property. At first glance, dual nature is absurd and impracticable. This seemingly implausible concept is referred to as the wave-particle duality. Here I will take the liberty of employing an excellent analogy to comprehend wave-particle duality. Imagine a cylinder. At one cross-section, its geometric projection will be circular, whereas, at the other cross-section, its projection on the screen will be rectangular. But then again, one way or the other, it's both. One perspective alone cannot completely describe the cylinder. In fact, it's both, together. Ready lecture notes and study materials are available on request. Please use the comments section below for further academic discussions. Viewers' suggestions and ideas of new video lesson topics are gratefully appreciated. Stay tuned for more uploads. Please remember to like, subscribe, share,